Hello and welcome to my presentation on this year's IKEA about bio-based pyrrolidones from succinic acid. I'm Benedict Winter, and let's just get right into the presentation. I think there's a problem we're all aware of, and a lot of our research is related to this, which is that we have a fossil-based chemical industry, which we kind of don't like anymore, and we would like to base it now on more sustainable resources. And there are actually quite a lot of ways to get from bio-based resources, for instance, to our chemicals, and quite a lot of research is done. I think it's quite a natural question at some point to ask, is the route I'm looking at actually better than what we're doing right now? And with this question, also this project and this cooperation started, and this talk, which resulted in this talk, which is that our colleagues from ITMC in Aachen, they looked at bio-based succinic acid and thought, well, what can we do with that? And they found a reaction where they could combine it with monoethanolamine to AGP, and then finally to N-vinylpyrrolidone, which is a product used in pharmaceuticals and cosmetics, and you can make polymers out of this. So this is a value product, and our colleagues at ITMC, they found a new route to get there based on bio-based materials. They wrote a very nice publication about it, but then the question came, well, we now have a new route, but is it actually better? And this is where we come into the picture. Who are we? This would be the chair of technical thermodynamics, also in Aachen, or now at ETH Zurich, because we kind of moved university in between. And we came there to help answer the question, is it better? And better is a bit elusive and a bit not concrete. So the question then came, is it better than what? And here we want to look at the fossil-based production. So is it better than the established fossil-based production route? And the next question, is it better for what? And in this talk, we will look at the environment and very specifically the global warming. And then when you look at it, if it's better, then the next thing you would like to do, well, can we even learn something more? And maybe we can learn something about the catalyst improvement, on how to improve the catalyst if we look if it's better. Okay, well, what do we now have to do? We have to do a life cycle assessment, and for that we actually have to know basically the mass and energy flows of every single process step in this production chain. And while this task might seem daunting at first, basically up till succinic acid and GBL, this was already done in literature, which means we only have to focus on the really exciting new parts, which means our new reactions. And to then get the mass and energy flows for these new reactions, we actually have to conduct some conceptual process design to establish the mass and energy flows. And because we're lacking a bit data down here in the fossil chain, we also did some simulation, but there the processes were based on available patterns. And I would like to talk about the first challenge we had, which is the process design for this first reaction step. Okay, if we now have a look at this process, we can see we have our reactants, hydrogen, monoethanolamine, succinic acid, and water. And in our first step, we just bring them up to reaction pressure at 200 bars. And then we heat it up to reaction temperature, 200 degrees Celsius, and we react them. And because in the lab, there was an excess of hydrogen, we also transferred this excess of hydrogen to a process simulation, which is probably erring a bit too much on the side of caution, but we stuck quite close to the lab in our process simulation. So there's a hydrogen recycle here. And if we now have a closer look what's actually going on in the reactor, we have our main reaction going on, which is our monoethanolamine plus the succinic acid reacting to our AGP. However, this main reaction only has a selectivity of around 71%. And there's a bunch of side reactions going on. The first group of side reaction is that our monoethanolamine and succinic acid are reacting with additional hydrogen to any of these four subspecies, or with a selectivity of 9.5%, or that our succinic acid is reacting just with hydrogen to any of these compounds with a selectivity of around 4.5%. However, if you add all of these numbers up, you see that we just have 85%, so there's still something missing. And the question now is, what is this? What we know about the lab here is that the missing 15%, so the carbon, what we know about them is that it's a heavy boiler. We know it's not extracting into dichloromethane. We don't know much about its thermal stability, and it probably is some form of oligomer. This was already proposed in literature, and these are some possible structures which are proposed for it, but they're not quite known. So now that we know what's going on in the reactor, we can actually see what we're dealing with at the end of the reaction section. What do we have? We have the gases, hydrogen, methane, ethane. We have the light boilers, which are actually mainly water, and then all our side products are luckily light boilers. We have our product, AGP, and then we have the oligomer. And now we want to get some pure product, which means we have to do some separation steps. And because we're not quite sure about the physical properties of the oligomer, we decided to simulate two different separation sections, one based on distillation and one based on extraction. And I will now first talk about the distillation section. So when we start the distillation, we actually lower the pressure here actually to 0.1 bar. We purge the gases. And then we have a first distillation column where we separate the oligomer. We have a very low pressure, so we don't have to get too hot in the bottom of the column from our side and main products. And then in an additional distillation, we can separate our side products from our AGP. So that's, I think, pretty straightforward separation section. For the extraction, we still have the gas purge, and then we have our extraction column with DCM, which is extracting our products from the water. However, here we are starting to face problems, and this problem we are having here is property data simply. We have quite a lot of different components, and if you look into Aspen, you will find property data for the gas phase for most of them. But once we come to the extraction, we actually need the liquid-liquid binary interaction parameters, and these are much harder to measure. They're much less available. And in Aspen, basically liquid-liquid data with water is available a bit, but not a lot. And liquid-liquid data with DCM is basically not available at all. And here, luckily, our chair also deals with predictive thermodynamics, and specifically a colleague of mine, Lawrence, does. And he was so nice to use the Cosmo model, where you use the chemical structure of a molecule to calculate surface charges of this molecule. And you can then combine it with some statistical thermodynamics to actually derive the property data. So we use this Cosmo model to calculate our property data in the liquid-liquid interaction. And with that, we then actually have all the data we need for the extraction column. Well, I say all the data, I mean all the data, of course, except for the oligomer. And here we're still faced with a problem because we don't know the structure, we don't know the size, we can't really model it at Cosmo. The only thing we really know about it is that there's no indication that it actually extracts into DCM. But the question is, will it be similar in the process? And we now decided not to just cut it out of the process and let it disappear. But what we did now as a proxy is we modeled the dimer in Cosmo and used this dimer as an approximation of the oligomer in the process design. However, we have to keep in mind that this is just an approximation. But the first thing we actually see when we use this approximation, and I think this is quite encouraging, this is that the dimer actually likes to stay in the water and gets mainly flushed out in the wastewater. And only 15% of the DCM actually lands in the extract, while virtually all of our product is in the extract. So this already indicates that the lab results are somewhat true. And if we then continue with our process design, well, we have one column to recycle the DCM. We have one column to separate our oligomer or dimer in this case, and we actually recycle that in front of the extraction because there's quite a lot of product still in there. And then we separate the side products from the AGP. So this is the design of the extraction process. If we now look at the overall picture again, we want to establish the quality of these two routes. We now got the data for this one process step. We still need data for the AGP to NVP step and also for down here a bit. So if we now look at the dehydration of AGP to NVP, what we actually see is, this is quite straightforward. You put the AGP into a nitrogen atmosphere, heat it up quite considerably, put it through a gas phase fixed bed reactor, let the reaction run its course. It gets dehydrated to NVP. It has a high selectivity. There's one side reaction going on. And then you can use a flash to recycle the nitrogen and 2 columns to separate side products from our NVP and get pure product. If we look at the fossil-based production now, we can start at GBL, we take some ammonia, we take some acetylene, and we turn this into NVP. And I will not go into any more detail about this. We did Aspen simulation, and they're based on various patterns on this process. There's nothing much exciting going on here. If you look at the overall picture again, we now have actually all the data we need to model both supply chains and then hopefully come to some conclusions about the merit of the new bio-based route. So what we're seeing now here is the global warming impact cradle to gate for the fossil-based supply chain as well as our bio-based supply chains. And what we see is that the fossil-based supply chain has an impact of around 6 kilograms CO2 per kilogram NVP, and the bio-based supply chains are actually just slightly lower. Another detail is that the succinic acid is produced with corn as feedstock. Keep that in mind. And if we now look at the contribution of the individual impacts, we can see that the educts are actually, or the reactants are the majority of impact in both cases with around 90%, and the utilities only make up about 11% of the overall impact. And what this probably already tells us about the catalyst development is that yield, prioritizing yield is probably much more important than prioritizing less harsh reaction conditions, because higher temperature would take up more utilities, but they don't really matter that much right now. Now, still, we are, of course, with 6% reduction in global warming impact, we're not quite yet satisfied, and we can now have a small look, can we actually do something to increase this? I told you before that we use corn as a feedstock for the succinic acid in this first case, and corn is actually quite a high impact feedstock. There are quite lower impact feedstocks available, sugar corn or corn stover maybe. And if we use this more sustainable feedstocks, what we can already see is that the impact of our bio-based production route is dropping significantly, and we can now expect reductions in the range of 22 to 28% for sugar cane or 38 to 44% for corn stover. So already just changing the feedstocks gives us the opportunity to increase our reductions. And in the slide before, I indicated that improving the catalyst might also be a way to reduce our impact. And here's some new exciting science is basically just in that in the original publication, ruthenium catalyst was used with the 73% yield, and Moritz continued working in the lab, and they now developed, or they're now using a platinum rhenium catalyst where actually yields of 83% are achieved. So the yield increased quite significantly. And if we now basically hotfix this into our process simulation, we can see that just by improving the catalyst, sticking with the high impact feedstock, we have a reduction of 30%. And if we change the catalyst and the feedstock, our reductions get up to 60%, which I think are quite significant reductions, already worth talking about. So if we quickly look back at what we did today, we started out with the question, is it better? And for that, we looked at our complete value chain, and then we identified some gaps in this value chain and used process simulation and predictive thermodynamics to close these gaps. And I think in the end, hopefully I could convince you that there's actually some potential for us to be better than our fossil-based route. And what we could also learn from this is that I think for the specific process, increases in yield are more important than actually less harsh reaction conditions. So this has been it from this talk. I want to say in the future, we're planning a publication and where we will also look into economics and other environmental impacts. That has it been for me today. If you have any question and if you're in my session, then please feel free to ask me right after this talk. Otherwise, feel free to contact me at any time and maybe we can just schedule a meeting during the IKEA. I am generally available and would be excited to discuss this more with you. Thank you for your attention and have a great day.